Howdy. How are y'all doing? Adequately caffeinated? That was unpersuasive. Okay. All right. So this morning, by morning I mean 1 p.m., 1:30 p.m. We talked about. Am I on the same planet?
Some people have come from.
I'm from LA, so I don't have an excuse. All right, so this afternoon, we started talking about the use of algorithmic randomness to solve linear algebra problems, and we saw a couple paradigms which are useful. The first one was random initialization, where we start an algorithm at a random point to ensure a favorable trajectory for the algorithm. The second thing we saw is a progress on average paradigm, where at each step of the algorithm we make a random choice to try and reduce the error on average. Now, this afternoon, the second part of the afternoon, we'll talk about some more themes. We will stop when we run out of time. There are a bunch of things we can talk about. The first thing I want to discuss is Monte Carlo approximation, which, as we talked about earlier, is one of the oldest types of numerical algorithms from the computer age. And it was only somewhat later that it was understood that these algorithms have a happy application to some linear algebra problems. So I'm going to start with the simplest examples, which are scalar, and then we'll talk about a matrix problem afterward. So the goal of a Monte Carlo method, this is a bit different from a Monte Carlo style algorithm. This is more along the lines of the classical Monte Carlo algorithms developed by Ulam and Metropolis. So we're going to try and approximate a hard-to-compute scalar quantity via the average of inexpensive random estimates. So the example we're going to discuss to illustrate this paradigm is called implicit trace estimation. So this is a beautiful problem that has actually a wide range of applications, but is maybe not very well known. And there's something which is a little bit surprising about this, because you probably think to yourself, how hard is it to compute the trace of a matrix? So I want to emphasize that we're going to put ourselves in a situation where our hands are tied behind our back, and that this is actually a difficult quantity to get your hands on. So we're going to let A be an m by n Hermitian or symmetric matrix. And we are going to assume that we can only access this matrix via matrix vector product. So what does that mean? It means that for a vector x, we can compute AX. And this is the way that we interact with the matrix. We can't ask it questions like, what is your 3-2 entry, unless we can frame it by asking, what is your second column, and then looking down that column for the third entry. Okay? So we have to pay for one matrix vector product every time we interact with the matrix. Okay? And you might wonder, you don't want to do it n times. Of course, if you do, you know the whole matrix and you're happy. But you should assume this is a moderately expensive operation. And so the matrix is a little bit unknown to us. So why might this be a reasonable primitive? So one typical example is that you want to solve a sparse linear system to get the action of the matrix A. This comes up a lot in numerical PDE. It comes up in the original application of the method I'm going to talk to you about, which is smoothing splines for statistical data. But if you imagine that A is not some explicit matrix, but in fact is obtained by solving a linear system, it's like really B inverse for some other B, you can start to see why this might not be trivial to access individual entries. Okay. Another situation we saw already was, what if A is a product of two matrices, B and C? Well, you could form the product B and C, but it would be a lot cheaper just to multiply repeatedly by a vector. Okay? So we are going to make this assumption, and the goal is to approximate the trace of A, which is the sum of the diagonal entries, with the minimum number of matvecs. So when I say minimum number, I don't mean this in any sense of optimality. Mostly that our algorithmic design goal is to try and control this number as well as we can.
What kind of number would make you happy?
Constant,
Constant?
20.
Okay. That's
Would that make you happy? I'll show you can do it with 32. Okay. So here's the idea. There's a Monte Carlo estimator. This is a great question. I mean, what's good? I mean, in this case, we can actually get something non-trivial with a constant number of these primitive operations. So the idea is to develop a Monte Carlo estimator. And this idea has its roots in the physics literature, but it was really proposed explicitly by Girard in 1988 and 1989. And then there was another very well-known paper by Hutchinson in 1990 that I think really popularized this idea. So here's the idea. We're going to look for an estimator for the trace using algorithmic randomness. So here's the simplest version of this. We're going to draw X from a standard normal distribution. And this ensures two things. If we compute the matvec AX and then take the inner product with X, this is exactly equal to the trace of A. And this is the mathematical expectation. Okay? This is an exercise for you to check that this is true. It's because normal vectors are isotropic. So XX transpose has as its expectation the identity matrix. But I'm going to leave this to you to verify. And a harder calculation, which will play a role here, is that the variance of this quantity is equal to twice the Frobenius norm of A. Okay, so what does this mean? So if I draw one normal vector and I build this quadratic form using one matvec, I get a random variable, X transpose AX, which is an unbiased estimator for the trace. Okay, it's probably not a great estimator because the variance looks like this, which can be related to the trace because this is positive semi-definite. So this is like twice the operator norm of A times the trace of A. And so you can see that up to this factor here, there is some comparability between the variability of this random variable and its mean, which is the thing we're trying to estimate. Now, it's typically not the case that doing this one time is going to solve our problem. So yeah, Raphael.
How did you get this Suss inequality for A having 0 in the diagonal?
Sorry, what?
I think he's assuming A is positive.
Sorry, A is, let's just assume that A is PSD. Thank you. I think there was a typo here in my notes. You're absolutely, oh, no, it's a typo on the board. We're going to assume A is PSD to make our lives easy. Thank you. Okay, where were we? So is one of these guys enough? The answer is probably not. So what are we going to do? It's already on the board. We're going to repeat and we're going to average. Okay, it's sort of a flavor of majority vote, right? So we're going to reduce the variance by averaging. So our trace estimator with S samples is going to be defined as 1 over S times the sum from I equals 1 to S of xi transpose AXI, where the xi are IID copies of the vector x. So in other words, we're going to draw these standard normal vectors independently. We're going to form these empirical estimates for the trace, and then we're going to average S of them. Good. So the hope is that with not too many samples, we can get a good bound. And the analysis is not hard. It's on your homework. So for example, with probability greater than 3/4, the empirical estimate of the trace minus the actual trace is less than epsilon times the trace, so this is a relative error bound, when the number of samples S is greater than 8 epsilon minus 2. Okay. So you prove this with Chebyshev's inequality. It's a very easy calculation, and I've even made some further estimates so that the bound is clean. So what this tells us, if I want to get something that estimates the trace within a factor of 2, I only need 32 samples, 32 matvecs to do that. And that's pretty likely to be accurate. And so maybe this is surprising, right? Because this is a big matrix. I mean, n could be 10 billion. And yet, if you can compute just a constant number of matvecs between the normal vector and this matrix, you can get a non-trivial estimate for its trace. Good. Any questions about the proposal for the estimator or the outline of the analysis? He was a statistician. Yeah, he was interested in computing smoothing spline or cross-validation for smoothing splines, and to do this, you need to solve a Laplacian linear system, which is very sparse. The Laplacian is the smoothing part, so you're trying to solve a least squares problem with a Laplacian regularization, and to compute the correct smoothing parameter, you need to perform cross-validation, which involves solving the sparse linear system. And so you do that by Cholesky factorization, triangular solves. It's cheap, but you don't actually have the matrix you need in your hands. Yeah?
Speak a little on what goes wrong when it's pleasant, when it's not positive and indefinite. Why was that required?
The trace could be 0. And so this is definitely not true, as Raphael has warned us. Yeah. Yeah, you get a bound. It's just not relative error anymore. You can't get something relative to 0. Yeah? Okay, good. More questions? All right. So it's pretty cool that you only need a constant number of samples. On the other hand, we also see the curse of Monte Carlo, which is that we are paying epsilon minus 2 to drive the relative error down. So if epsilon is equal to 1/10, S is greater than 800, according to this analysis. If you want to make epsilon 1/100th, 1% error, we're at 80,000. 80,000. Yeah, that makes us very sad. And so the point here is that you cannot hope to get an accurate estimator using a Monte Carlo method. And for this reason, numerical analysts have historically loathed Monte Carlo methods because you're stuck with limited accuracy, even though they're very powerful tools. Okay? So have you seen estimators like this before, perhaps in your numerical analysis class? What do we use these for? For quadrature. We use it to compute integrals, especially in high dimensions. And this is effectively the same problem here, but deployed toward a linear algebra application. Okay, so I assume nothing. Now, to come back to this cursive Monte Carlo business, if you actually want to do this in practice, you really need to use variance reduction techniques. So it's not enough to use this type of simple estimator. You have to work harder. And when you ask, how could I do this, you remember that this is a random variable. This is something you can apply statistics to. Statisticians know quite a lot about Monte Carlo methods and about empirical estimators. And if you dig through the statistic literature, you can find ideas about how you can make the variability better and reduce the cost. So one idea is something called a control variate, which asks you to find another random quantity, which is easier to compute, but is well correlated with the trace. I'm not going to talk about how to do this, but there is a lovely paper by Raphael and company, which develops an estimator called Hutch++, which incorporates a variance reduction strategy that gets this cost down to epsilon minus 1 in the worst case, which is a huge improvement. Okay? So without variance reduction, you're stuck with the cursive Monte Carlo. It makes you sad because you can't get high accuracy. But with variance reduction, you can improve the dependency on the desired relative error and get really highly performant algorithms. I will also mention another paper we wrote on an algorithm called xtrace that layers on even more variance reduction to get even better estimates. So these are both examples of using ideas from statistics to improve the simple Monte Carlo estimator for what's really a basic problem in linear algebra. Some other things that people like to do are counting triangles in graphs. So this requires you to compute the trace of A cubed, where A is an adjacency matrix. You don't want to form A cubed explicitly, but you can apply A to a vector efficiently 3 times and run the estimator. There are examples in chemical graph theory. There are examples in quantum information science and quantum physics. There are lots of things that boil down to trace estimation. This is not just like some made-up problem. OK, questions about this first Monte Carlo method? So there are more examples of scalar Monte Carlo. So people use this to estimate norms. So there's an overview of some of the results in MT20. People use this for spectral density estimation. So our density of states, sometimes called. There's a nice paper on this by Kong and Valiant from 2017. And it also comes for estimating trace functions. So there's an algorithm called stochastic Lanczos quadrature, which is due to Golub and Mirhan. And there's a nice paper on this by Ubaru, Chun, and Saad from 2017. All right, so the scalar Monte Carlo paradigm has a number of applications in linear algebra, but it's not limited just to estimating scalar quantities. This kind of averaging approach works in any linear space, and in particular, you can use it to approximate matrices. So that's going to be our next task. So the next application is matrix Monte Carlo. So B, matrix case. The goal here is to approximate a complicated matrix as an average of simple random matrices. So I'm going to describe a somewhat fake application just to give you an illustration of the flavor of this idea. And I'll mention a few other applications when I'm done. So the example I'd like to look at is approximate matrix multiplication. So a lot of our discussion this week has been about how to exactly compute products of matrices efficiently. But what if you're willing to give up on the exactness? You're willing to accept something that has sort of the flavor of the matrix product, but is not precisely correct. So here is a simple setting where you can frame this question. So we're going to let A be an M by D matrix, where now D is much bigger than N. So this is a fat matrix, lots and lots and lots and lots of columns. And our goal is to approximate the product B equals A transpose, which is in R N by N. So this is a little matrix. And the nominal cost, if you use the standard matrix multiplication algorithm, is order n squared times d. Okay? And d is a big number. So you should think about n as being maybe tens or hundreds, but whereas where d is on the order of thousands or millions or something. Okay? And so you're perhaps willing to accept an approximation for this matrix B rather than insisting on the precise product. And the hope is that you can do that in fewer operations. Okay, so there's a Monte Carlo algorithm for this. Which seems to have been proposed originally by Ravi Kannan and Petros Draneas. So I should erase Girard here. So this dates back to about 2001. And so Petros and Ravi noticed that you can write the product AA transpose as the sum from j equals 1 to d of AJ transpose, where now the AJ are columns, not rows. And once you see a sum like this, one of your instincts as a computational mathematician should be to approximate this empirically, sums and integrals. And here's a simple way we can do that. We can design a random matrix X, which takes the value Pj, AJ transpose, with probability Pj for each j ranging from 1 to d. Okay? So this is a rank 1 random matrix. With some probability, it picks out the ith column from A and forms this outer product, and then reweights it by the probability. I haven't told you what the PJs are yet.
No, but isn't this cost d squared to get these AJ transpose?
No, it's n. These are m by n. So the matrix here looks like this.
Oh, there's d of them.
So this is n. This is d. Yeah, no problem. Yeah, it's hard to keep track of dimensions without a picture. I should have drawn this for you. Oh, whoops, I got it backward. Ignore that. N, D. Oh. Okay, this is the hard stuff. What? Are we good now? Okay, so these guys are just m by n, so forming one of these explicitly costs n squared operations. And yeah, so you should check that the empirical average of this matrix X is exactly equal to AA star. And this is just the law of total probability, which you... sorry, what? Oh, yeah, there should have been an inverse. Thank you. You would think I could copy things from my notes onto the board, but this proves insurmountable most days. Okay, so do you think that this rank 1 matrix is a good approximation for B? Probably not. Because for sure X has rank 1, and it's reasonably plausible that B has full rank. It's got rank n. So you can't approximate a rank n matrix with a rank 1 matrix, so what are we going to do? Yeah. We're going to repeat and average. So we will improve by averaging. So let's write that down. So we have a matrix BS hat, which is defined to be 1 over S, sum from I equals 1 to S, xi, where the xi are IID copies of x. So we'll just sample these repeatedly, average them, add them up, divide by the number, and we hope that BS is a better approximation.
But it's still not going to be full rank.
Well, unless S could be bigger than n, but remember D is much, much bigger.
But then we're at n cubed D.
No, no, it's n squared times S.
Oh, yeah, but I'm saying if you're taking S equal to n.
Yeah, but n is smaller than D, right? So, yeah, right. So I admit that this changed from the previous n and D, but that's the picture you should keep in mind. Okay? Good. N squared S is a lot smaller than n squared D, I assert. Now, there's one more ingredient, which is how we choose the probabilities. And once again, we need to use importance sampling because some of the columns of A might be more important than others. So here's an importance sampling distribution. We can choose Pj to be the energy in the jth column as compared with the total energy in A. Now, this will cost you ND if you have to compute these things. There are applications where you know these things a priori, and so you don't have to do any work. So for you, my friend, this is free. Okay? So we have an importance sampling distribution, which tells us that we should choose columns in proportion to how much energy they have in the hope of putting our emphasis where we need to. And we can analyze this using a it's not like these erasers have moved, and I can never find them. Turning around in circles, like I'm completely bewildered. I mean, I am completely bewildered, just sort of as a matter of course, but. Okay. So the analysis of this uses a result called the matrix Bernstein inequality. A reference for this is my monograph from 2015. And what we can see is that the spectral norm error in approximating the product is less than or equal to epsilon times the spectral norm of B squared. When we take how many samples? S should be bigger than 4 epsilon minus 2 n. This is the worst case rank. And we need a log factor to help deal with the spectral norm. Okay? So as we discussed, we think that B might have rank n. And so it's reasonable that we need to add up n rank 1 matrices to have any hope of approximating it. And once again, we see the Monte Carlo rate of epsilon minus 2. If we want very high, or if we want the relative error epsilon to be small, we have to pay a lot in the number of samples. So you should not hope to get a good approximation this way without working for it. And then there's a slop factor, which allows us to deal with the spectral norm. Okay? But once again, if I were willing to take epsilon equal to 1/2, say, which is a non-trivial approximation, this constant is 16. And that's independent of D, the total number of columns. So, and as we saw, the cost of this is order n squared S versus order n squared D. And There's no dependency on D here. Okay, so this is what the Monte Carlo buys you. You have to make a mistake, but it's a lot cheaper. Yeah, Yoav.
So the difference of the norm, like norm of the difference is dependent on the norm squared? Like
You're absolutely right. It should be homogeneous. Thank you. More questions?
Bit J's are already this, so how do you, so it's going to be that small, no?
Okay, so the question is, where does your matrix come from? If you believe that your matrix is full of data and you have to compute this, you have to pay for this. If, on the other hand, the matrix describes some physical process or comes from some construction that you understand, these numbers might be free to you. There are settings where all of the columns have the same norm, in which case this is free. So whether or not you need to pay for this depends on the problem you're trying to solve. The fact is that this is not a real algorithm, in the sense that this is not the kind of thing that we typically use directly for its own purpose. It's a building block for other things, and it illustrates a principle.
But ND is also smaller than n squared d.
Sorry, what?
ND is still smaller than n squared d. So even if you do pay to compute,
Yeah,
you won something.
you've won something sometimes. It depends on how big D is, right?
Yeah.
How much you've won. But yeah, ND is definitely smaller than n squared D, I think.
If it's positive, semi-definite.
Yeah. N's bigger than 1, right?
Fractional times.
Joel, I have a question.
Yeah.
So you keep repeating this, so I have some idea of the distribution. Are there results which are robust in the sense that if you only have an approximation of that?
Yeah.
What kind of keywords will you find these results?
I'm not sure that it's been written out explicitly, but the way these kind of arguments work, if there's some mismatch in the distribution, you're going to pay for the mismatch. The number of samples is going to be a bit bigger, depending on how big the mismatch is. This is somehow the right distribution for making this work. Yeah. All right. Good. So let me just mention a few related methods that are based on something similar. There is the matrix sparsification result of, this goes back to Cleoptus in 2001. It was, I think, well understood by Kundu and Droneus. The idea here is that you have some big matrix. You'd like to approximate it by a sparse matrix without losing very much in the spectral norm. And they found a method for knocking out a lot of the entries in the matrix without destroying it completely. Whether or not you can do this depends on how close the matrix is to low rank. For example, you can't approximate an orthogonal matrix by a sparse matrix in general, but you could approximate a low rank matrix by a sparse matrix. This comes up in graph sparsification. So Nikhil and Dan have a very nice paper from 2011 where they show that if you sample the edges of a graph in proportion to their conductances, that you can reduce the number of edges in the graph to the number of vertices, roughly, while preserving the spectral properties of the Laplacian.
Yeah, so what properties of the matrix do you want to be preserved when you sparsify it?
It's the same thing as here, right? So you want to approximate some matrix B by a sparse matrix with, say, S non-zero entries, and you want to approximate it in spectral norm. So the spectral norm ensures, the operator norm ensures that all linear functionals are similar, all eigenvalues are similar, eigenvectors associated with well-separated eigenvalues are similar. This is a very strong claim. There are a lot of things that come from this type of error bound because the spectral norm controls everything. So you can use perturbation theory. Yeah.
So if you have a rank 1 matrix, what sparse matrix works best for that?
I'm not sure that this is something that I can produce for you off the top of my head, but what will happen is that the sparsity level will be proportional to n, and that's it. So you can approximate a rank 1 matrix by a matrix with about n log n entries.
Roughly a weighted expander.
Yeah, yeah. Yeah. I think it's better to look at the papers but again, I don't know whether there are like real applications of this or not. I think the idea was like nominally compression or something like this. But I haven't seen convincing applications. I'm just mentioning that there are other problems that are described by matrix Monte Carlo approximation, which may or may not be useful. A couple more. This is my favorite, the sparse-Cholesky algorithm of King and Sakdeva computes an approximate Cholesky factor of the Laplacian of a graph by repeated sparsification of the Cholesky, of the Schur complement in the Cholesky step. This is a real application of sparsification. This comes up in random features approximation. There's a paper by a bunch of people from 2014 that works this out. You can use this to study quantum tomography. Anyway, there are a lot of problems that fall into this category, some of which have contemporary scientific interest. This is Gutta 20. Okay, so matrix Monte Carlo, the idea of approximating a complicated matrix by an average of simple random matrices, has a wide scope of potential application. And this is sort of a template for what these models look like. And the key idea behind the analysis is to use matrix concentration inequalities. Okay, questions on this?
What is sparse Cholesky? You say the problem is?
The problem is to take the Laplacian of a graph and produce an approximate Cholesky decomposition, which is a factorization CC transpose, where C is upper triangular, and has very few non-zero entries, and yet approximates the true Cholesky factors of the Laplacian.
Sparse the matrix because it's coming from the graph.
The sparsity is proportional to the number of non-zero edges in the graph. So for sparse graphs, it's very sparse. Even if it happens to be dense, the algorithm is still much faster than you would anticipate. Yeah, yeah.
Cholesky decomposition, I mean not the true one, but
Yeah, you're willing to, because you're going to use it as a preconditioner.
quite
Yeah.
fast.
Yeah, you're going to use it as a preconditioner. This is something that's probably best for us not to talk about in detail because it's a sophisticated algorithm. These are just keywords. My purpose in writing this on the board is to alert you that this idea is not some one-off that was designed for a problem of relatively limited interest. It is a beautiful idea that has a wide range of applications in computational mathematics, some of which actually lead to state-of-the-art algorithms. So that's my message here. Yeah?
What's the probability of success for this algorithm?
You can write down probability bounds, which are like log 1 over delta types of things if you want failure probability delta. I like writing down the expectation because concentration tells you that the expectation is the typical behavior, not just the average behavior. Yeah. More questions? Okay. So what I'd like to do with the dwindling time we have remaining is to give you a very high-level overview of some other ways that people use randomness for regularization. And so this is going to be even sketchier than the examples I've already done, because I'm just trying to give you the gestalt. Okay. So regularization. At a high level, the idea is to randomly transform a problem to make it easier to solve. So there are a lot of wonderful examples of this. So one class of examples falls under the category of what you might call general position. The idea is that you're going to take a problem instance and transform it into another problem instance, which is equivalent, but somehow avoids all of the failure modes of the algorithm that you want to use to solve the problem. No, it's not the same. I can draw the distinction in a minute. I will be very explicit about what I mean here. General position means different things in different contexts. The example I'm going to give comes from a paper of Daniel from 2023. So here is a problem. Consider symmetric matrices, A and B, that commute. So that means that AB is equal to BA. And we know that commuting self-adjoint matrices are simultaneously diagonalizable. And the goal is to find the orthogonal matrix Q that achieves that goal. So we want Q transpose AQ and Q transpose BQ to be diagonal. Same Q. Okay. You know well that by the spectral theorem, you can do this for one of the guys, but when they commute, you can do it for both of them at the same time. Now, this is actually not trivial, because if you diagonalize A, there's no guarantee that the Q you get also diagonalizes B. You have to do some work to make sure that happens, because there are possible degeneracies. And the insight, which is in this paper, is that you can achieve this goal with the following artifice. You take a random linear combination. That's exactly right. Here. Okay, so the idea is exactly what you just said. Form a random linear combination. So we will form C, which is gamma 1A plus gamma 2B, where the gamma I are IID standard normal random variables. And so this is some point on a plane connecting A and B, not necessarily on the same line. And what's remarkable is that when you diagonalize C, you get the desired basis Q with probability 1. So the only places where this goes badly are a set of measures 0 in this plane. Okay? And so what we've done here is that even though A or B could be bad, there might be combinations of A and B that are bad, a generic combination is always good. Any, what?
There's only a finite number of that.
Yeah, yeah. Yes, and so in particular, you're not going to hit any of them this way. This,
So is it
yeah.
is part of that C could still be bad, but it can only be bad where A and B are bad in the same way?
Yeah, so what happens is the only way C can have a repeated eigenvalue is if that comes from repeated eigenvalues of A and B with the same common eigenvectors.
Right.
That's the only thing that can go wrong, but then, anyway, there's no problem. This is on the homework. Part of the reason this paper is interesting is that this actually works even if A and B only commute approximately, even if there are like 30 matrices that approximately commute with each other. There's a lot more going on here, but this basic principle tells you that this random combination somehow avoids all of the possible issues that could occur if you took A and B and they happen to be unfortunately aligned.
Joseph said it, but I'm not sure I understood. So if I would take a convex combination, not random, like gamma, A plus gamma, comma b, is there only a finite number of comma by
That's what Joe just said, yeah.
Yeah, I got. Now I understand.
So, yeah, Nikhil.
In this algorithm, do you have to prove some lower bound on the gaps of this random?
I think that to analyze it in the inexact case, you actually have to do some perturbation theory. But for the case where they commute exactly, this is straightforward. It's really just linear algebra. Anyway, this is a very beautiful algorithm. And this is an illustration of what I mean by putting the problem in general position to avoid any unfortunate outcomes. So there's some related methods. So one of them is randomized Gaussian elimination. So if you have a matrix and you rotate it randomly on both sides, you can run Gaussian elimination without pivoting. And with probability 1, you will never encounter a 0 pivot. So this idea is due to Parker from 1996. There's also the randomized URV decomposition, which Holt. Yeah, this is a straightforward fact about, polynomials, really. Like the determinant of a principal submatrix is anyway. So this is not hard to prove, but it was an insight. And you can avoid pivoting entirely. And then this was analyzed more carefully by Demel-Dimitriou and Holtz, where they actually obtained rigorous bounds on what happens and showed that these things allow you to produce strongly rank-revealing decompositions. So and all these are examples of putting a matrix in general position to avoid bad things that could happen. Good. Any more questions on this? No, the idea is that you take the matrix A, you multiply it on both sides by Haar unitaries, and that resulting matrix allows you to run Gaussian elimination without any pivoting at all. Yeah. So you're basically changing the basis for the row space and the column space at random. Yeah. 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 Yeah, the set of bad matrices is measure 0, so I mean, yeah. But that a priori doesn't tell you the pivots don't grow. So you have to work harder if you want to argue that that's actually a sensible strategy. Also, it costs you n cubed time to do that. Or n omega, sorry. Since you asked about smoothed analysis, why don't we talk briefly about the application of smoothed analysis, just to draw the counter distinction, although Nikhil ably illustrated why this is got algorithmic applications this morning. So this is another form of regularization. So what is smoothed analysis? Algorithmic version. The idea here is that we will apply a random perturbation to a problem instance to improve its conditioning, or else to stabilize the algorithm that you want to use. So the example that I was going to describe is the one that Nikhil described this morning, which is pseudospectral shattering. And this is Banks plus what year? 22? 20? 22x. Okay. So in brief, we'll let A be an m by n matrix. And the goal is to approximately diagonalize and the way we do this is by random perturbation. So we'll form A sigma, which is A, plus sigma G, where G is a Ginebra matrix, IID complex Gaussian. And with high probability, A sigma is diagonalizable and has separated eigenvalues. Nikhil showed you the picture this morning, which you will never forget. It shows you that one eigenvalue splits apart into this set of petals, where each of the eigenvalues is well separated from each other and is stable, at least locally. And so the idea is that by applying a random perturbation to your instance, you arrive at a computational problem which is well conditioned and that you can reliably solve with a sufficiently clever algorithm that we did not learn about because we ran out of time. Okay, so this is smoothed analysis. And there are other applications of this, including smoothed analysis of Gaussian elimination, where if you randomly perturb your matrix, which is an n-squared operation, you're just adding a little something to each entry, you can ensure that the pivots don't grow too quickly when you perform Gaussian elimination. So there are other ways in which poking the computational problem might make it more favorable. This is different from general position because this problem of finding the diagonalization of A sigma is different from the problem of trying to find a spectral decomposition of A. It's not the same matrix anymore. We're relying on this artifice of using backward error analysis to make this okay. Whereas in the general position setting, we are literally solving the same computational problem. We didn't change anything. Yeah? Okay. One other thing that people like to do that I think I'm not going to bother you with is randomized preconditioning. So you can use a randomized algorithm to construct a preconditioner which makes your algorithm work better. And there are a bunch of examples of this in the literature. This is another example where you're not changing the computational problem, you're just making the algorithms faster. And so this is a popular technique that I thought Chris was going to talk about, but I think we did not have time.
I thought you were going to talk about it.
You thought I was going to talk about it. What can you do? Anyway, so part of my goal has just been to show you that there are lots of different ways that randomness has an impact on computational linear algebra. And I think that they're conceptually distinct. It's not, oh, I forgot to tell you about dimension reduction, but whatever, everyone knows about that. My notes are a mess. Anyway, there are a lot of ways that people can use randomization to solve linear algebra problems, and I imagine there are probably a lot more. And so I think one of my hopes this fall is to learn some new ideas from y'all. Thanks.
Surprising, finishing on time. Gives us time for questions, I guess. Yeah, Peter?
Again, back to the randomized Gaussian elimination. Now you explained to me you do a transformation. Unitary random, but it costs.
Oh yeah, absolutely.
So what's the goal? Is it to gain?
The idea is you're going to take A.
It's so costly to do this. So what is the purpose of doing that? The position or? Okay.
That's what you do, and then you apply GE to that. What's the point? Well, we are a lot better at matrix multiplication than anything else, and so this is actually not so bad. So you can do this. You can take advantage of Laws 3, and then you don't have to do any data movement because there's no pivoting.
Randomized hard would be
Then you
n
use
squared
the
log n, right?
decomposition.
Huh?
Right.
You do randomized
Yeah.
hard, it's n squared log n.
Okay,
Okay.
right. That was not Parker's proposal.
Okay.
So what Jim is saying is that if you choose U to be of the form Fourier transform times random diagonal, and same for V, you can use an FFT algorithm to compute this in order n squared log n, which pushes the cost much farther down and
Has that been formally
also
analyzed?
avoids the, what?
Has that been formally analyzed to do the?
That's a good question. Has it been analyzed? I mean, you might need to use.
Yeah, it makes sense that it works.
You might need to use Steinhaus variables or something to get a little bit of like non-discreteness. but
I think it's been honest just to say that you're probably one you're not going to get like 0 pickups.
I'm not sure because that argument relies on the fact that the roots of a multivariate polynomial are not everywhere. But yeah, the problem is if you use discrete distributions, you could potentially land on the set. A lot of this really depends on the properties of continuous random variables and how they interact with polynomials. Yeah. I mean, I believe that it works. The analysis is a different story, though. Yeah.
No, but like theoretical.
I don't think there's a theoretical analysis. Not for this purpose. Yeah, no.
So you said the reason people don't always do this in practice is just that the pivots still grow, and so you still do have to do pivoting in practice. I didn't catch that.
In
Why is everyone doing
practice,
this all the time?
in practice, you have to do partial pivoting at least, and that is the computational standard. We turned up a paper where people actually do something like this for some parallel computing reasons, and it seems to work.
So what this buys you is really the pivots, like the things aren't 0, but they're still growing, and that's bad.
They don't grow. So this is the analysis that the DDH paper is that if you do this, you can actually control pivot growth. Is that right? And at the very least, you can get a strong rank real decomposition. Did you analyze the algorithm too?
Yeah, we didn't do LU, we did QR.
You did QR. Okay, so there's no issue there. And probably you don't even need pivoting, right? Yeah.
So then the reason people aren't doing it is just that the matrix multiplications themselves cost enough that it's not worth it to avoid pivoting?
I'm not sure I'd say that people do this. People could do it.
I think he's wondering why do people not do this? Because that's what you're asking. Right? Why doesn't everyone?
Why do people do anything? Social and economic factors. In spite of our beautiful ideas, they were not cost effective.
I think Jim wanted to say some rational argument.
I was going to say, there's lots of ways to make pivoting go faster, and I'll allude to some of them tomorrow.
Thanks.
I can have a cultural note. One thing that took me a long time to understand about numerical linear algebra was that as opposed to like pivoting, you couldn't do QR factorization, and there's no growth equivalent, there's no issue. But it takes like what, twice as many operations?
4/3 instead of 2/3.
Okay, so they don't do it. So that's why then we care about pivoting and complicated analysis of Gaussian elimination. But like if you're a theoretical computer scientist, if you can do something simple and it only costs twice as much more, you're like, yeah, I'll do it. Simple, right?
Salary maybe.
Yeah.
Otherwise, yes.
In this context, constants matter.
The real world.
Awesome. Thanks so much for. Oh, there's one more.
Just curious, when you're talking about Monte Carlo estimation,
Yeah.
things like trace, estimating the trace, you alluded that you could do like variance reduction.
Yeah, there's a beautiful idea, which is there are a bunch of precedents, including work that Lynn did, but it's really crystallized in this paper by Raphael, Chris Cameron, and David Woodruff. The idea is the following. You use some of your matrix vector multiplications to form a low-rank approximation of the matrix. You can compute the trace of that low-rank approximation explicitly, and then you use the randomized trace estimator to estimate the trace of the residual. But because the residual is much, much smaller, it doesn't matter that you pay the Monte Carlo cost because you're estimating something much smaller, so it doesn't have to be so accurate. And this hinges on the fact that we're very good at computing low-rank matrix approximations from matrix vector products. So these are some of the most established algorithms in this area, although I didn't talk about them.
So at least one of the topics you mentioned, if we just set d equals n, actually the randomized algorithm has worse complexity.
Oh yeah.
And is this
at least
general
according to the
phenomenon?
analysis, yeah.
So is this a general phenomenon of?
Well, Yeah, so we're not so good at solving square problems using these randomized techniques. They're harder. It should also be said that there's an issue to do with probability, which is that if you wanted to sample every column of a matrix A that has n columns, and you just pick them uniformly at random, you need n log n draws before you reliably get all the columns. Okay? This is called the coupon collector problem. And this warns you that if you are sampling, there could be probabilistic effects that are pernicious, even though you gain some benefits from the fact that the estimator of the matrix is unbiased. But if you need to hit all the columns to get the approximation, it's going to take you a while to find that last column. Awesome.
Okay.
Thanks so much.